Hi, I'm Clyde Lee, Professor Emeritus in the Department of Civil Architectural and Environmental Engineering at the University of Texas at Austin. For the last 60 years, I've been involved with the development and application of a technology for weighing road vehicles without stopping them. Today, this technology is called Weigh in Motion, or it's known by its acronym WIM, or WIM. WIM is defined as the process of measuring the dynamic tire forces of a moving vehicle and estimating the gross vehicle weight and the portion of that weight that's carried by each wheel, axle, or axle group of a corresponding static vehicle. The design of the instrument system and the logic that has been used to implement this definition of WIM is based on a few fundamental concepts. It's important that users of WIM, and especially potential users of WIM, understand and apply these concepts as they specify, procure, install, operate, and maintain a WIM system at a specific site for a specific purpose. As part of this audiovisual informational series called WIM 101, 101 being the course designation system used in American universities to tell the level and content of a course's and a student's curriculum, I'm going to address some of these fundamental concepts. Road vehicles are usually weighed for one of four reasons. First, for commerce, where we buy and sell goods by weight. Second, for enforcement of weight and load limits of vehicles, which includes gross vehicle weight, axle load, axle group load, and sometimes wheel load. Third, to aid enforcement, to select suspected overweight or overload vehicles from the traffic stream for subsequent enforcement weighing with static devices. And fourth, for collecting statistical data that are needed to maintain and operate our infrastructure system. Now let's consider some of the basic concepts of weighing road vehicles. Concept number one deals with the use of the terms weight, mass, force, and load. The term weight is used today, as it has been historically in commerce, to mean the mass of a vehicle. Mass is roughly the amount of matter that's contained in an object. So to accomplish the weighing of an object or determining the mass of an object, the weighing devices, called scales, are adjusted at a particular locality where the force of gravity is more or less constant to indicate the value of field standard test weights. These are objects that their mass is traceable to the international kilogram standard that's kept in France. The term weight, however, is used in modern scientific terms to indicate the force of gravity acting on a mass. So to determine weight in modern scientific terms, we would simply multiply the mass that has been determined on the adjusted vehicle scale by the local acceleration due to the force of gravity. And that's a calculated product. In common practice, the term weight should be used only to refer to the gross vehicle weight of a vehicle. It should not be used to refer to the portion of the gross vehicle weight that is carried by a wheel or an axle group. The term load is used to define and describe the portion of the gross vehicle weight that is carried by a particular wheel, axle, or axle group, and should be used to describe that portion of the gross vehicle weight. The devices that are used to determine load are named axle load weighers and wheel load weighers rather than scales. Concept number 2 deals with how to weigh a static vehicle. I'm going to talk about weighing a static vehicle in WIM 101 because we use the static weight of a static vehicle as a reference value, and in fact the object of weighing in motion is to estimate the weight of a static vehicle. So to weigh a static vehicle for commerce, that is buying and selling by weight, a vehicle scale must be used. A vehicle scale is a device that is used at a particular locality and is designed with a load receiving surface sufficiently large to accommodate all the tires that support a vehicle at the same time or simultaneously. The platform has to be designed so that the signal or the weight indication is independent of where the tires are located on this platform. The devices that are used as vehicle scales today are tested and certified periodically using field standard test weights that are traceable back to the prototype kilogram. And the accuracy with which a vehicle can be weighed on a vehicle scale is within a tolerance of 0.2%. That's accurate to 1 part in 500. So these scales are used for commerce. To use the scale properly, the vehicle must be weighed at one time, one stop. It's called single draft weighing. So the value that is indicated by the commercial vehicle scale is a single draft weighing, and only single draft weighing may be used. A vehicle scale may have a single platform, or it may have multiple platforms that are linked together. And if we use a multiple platform vehicle scale, it is feasible to stop a vehicle on the multi-section vehicle scale and be able to determine axle loads and axle group loads at the same time we determine the gross vehicle weight. These scales are not common, but they can be used to determine load and weight and axle group weight. If a vehicle scale has suitable aprons around it so that it can support the tires of the vehicle that are not being weighed, then we can use successive addition of the different wheels and axles to determine the individual value of axle load and wheel load and axle group load. All right, to weigh a static vehicle for enforcement purposes and statistical data gathering purposes, we require different devices than the vehicle scale. We have to have load measuring devices to separate the portion of the gross vehicle weight that is carried by the wheel or the axle group. And these devices are not as accurate in their use because the vehicle must be moved from one position to another to position it on the device, position the wheels on the device. So every time we move a vehicle, the total weight is distributed differently among the wheels and axles. So if we weigh by parts, wheels or axles at a time, we're going to have more error than we have if it's weighed in a single draft. So this movement makes the device less accurate, but also the fact that these portable devices called wheel load weighers and axle load weighers have tolerances that are 2% rather than the 0.2% that we were talking about with the vehicle scale. So inherently, the devices and the weighments that we get are less accurate for these devices, but they're sufficient for enforcement and for collecting statistical data. So when we use these devices, it's important to minimize the load transfer that takes place and be sure that the devices are used to maintain the tires in the same horizontal plane whenever a weighment is made. When we think about the application of load measuring devices, static load measuring devices, we might ask the question, can WIM be used to supplement or to replace the use of these devices? The answer to that question is a qualified yes. When it comes to measuring the loads for enforcement, a weigh in motion is located at a particular site. It's not portable. And we can use the WIM, though, to identify suspect vehicles for subsequent weighing on the portable static devices. And this lets us use the WIM concept. With modern communication today, an enforcement officer can actually monitor the indications from a WIM system in real time, remotely, and then select that vehicle, identify that vehicle that is suspected of being overweight, and use the WIM to identify that vehicle. When it comes to collecting statistical data, weighing a vehicle on portable devices, load measuring devices, requires that the vehicle be taken out of the traffic stream and stopped and weighed and then reinserted into the traffic stream. It takes 2 to 10 minutes to accomplish this diversion of a vehicle to get a sample of one vehicle load values. WIM can operate at a particular site 24/7 without interruption and no adverse effect on traffic. I've often said that as a design engineer, I'd rather have a design wheel load or axle load that's accurate to within 10% plus or minus based on observation of 10,000 vehicles than to have an observation, a design value that's accurate within 0.1% based on the observation of one vehicle. So for statistical purposes, the value of WIM, being able to collect large continuous samples of data with reasonable and good accuracy, is very important and is an advantage to that, to help replace the values that have been determined so laboriously over the years with static weighing devices. Concept 3 deals with weighing a moving vehicle. The basic idea that makes it feasible to use a single tire force sensor to weigh a moving vehicle is that if we have an ideal vehicle, that is one that has balanced and round moving, rotating parts on the vehicle, and that ideal vehicle is moving at a constant speed in a straight line path on a smooth horizontal surface, the tire forces that would be generated, applied to the pavement surface, would be exactly the same as if the vehicle is standing still or stopped. This means that no component of the vehicle, while it's moving, is moving in the vertical direction. So the tire forces, whether the vehicle is stopped or whether it's moving, would be exactly the same. Of course, these ideal conditions are never going to exist at a real world WIM site, but we can minimize and approach minimize the difficulty and approach the ideal conditions if we select a site for weighing that has good road geometry, that it is straight and approximately level, and we can select the site so that the vehicle will be moving at a constant speed, more or less, and not accelerating. And then we can either select or provide or even construct a smooth surface that would minimize the vibration and vertical movement of the vehicle while it's passing over the WIM sensors. So the basic idea that we take a single sample of the tire force while the vehicle is moving under these nearly ideal conditions. Of course, we can neglect certain forces. I mean, aerodynamic forces are such minimal values for the moving vehicle that we can neglect those. But we can use a calibration procedure at a particular site using test vehicles of known values for weight and speed to calibrate the WIM signals that come out of the sensors, so that we eliminate any local effects of the smoothness of the pavement. And so the idea then that we can use the single tire force sensor is based on the idea of providing a smooth pavement. The user is responsible for providing and maintaining that smooth surface that makes this concept feasible. The WIM system supplier is responsible for processing the signals that are generated from the tire force sensors and other sensors to estimate the value of the static vehicle. Of course, the tolerances that can be attained by weighing a vehicle, moving vehicle, are going to be larger than they are for the static weighing. So this fact needs to be recognized when a user writes a specification for the performance requirements of a weigh in motion system. There are some guidelines in a document called ASTM, American Society for Testing of Materials standard, that give some reasonable and attainable tolerances that should be used in preparing a specification for a WIM system. Concept 4 deals with how a WIM system works. The essential element of a WIM system is the tire force sensor. Designing a suitable, capable tire force sensor is not a trivial matter. The first significant feature of a tire force sensor is that it responds only to the vertically downward component of tire force. Second, it is compliant. It responds faithfully and instantly to the applied force. Third, it does not oscillate once the force is removed from it. Fourth, it produces a signal that is linearly proportional to the applied tire force. Fifth, the sensor deflects under load similarly to the surrounding pavement. Sixth, it is insensitive to the tire contact pressure, the tire contact width, and the tire contact area and tread pattern. 7, it is insensitive to the lateral position of the tire in the traffic lane. 8, it is insensitive to moisture and temperature. 9th, it is minimally invasive into the pavement structure. And 10th, it is durable. It'll withstand millions of applied tire forces within its useful life. Sensors that include many or most of these features have been developed over the years. I demonstrated my first prototype WIM sensor in 1955. But the sensors that are available on the commercial market today are based on two fundamental technologies. One technology utilizes bonded resistance strain gauges, electrical strain gauges, bonded to a spring element in the sensor. And the change in resistance is measured when a tire force is applied to the surface of the sensor. The second technology involves the use of a piezoelectric material. This material generates an electrical charge when it is deformed mechanically. So if we use a piezoelectric material in the sensor, it generates a electrical charge that is proportional to the force applied to the surface of the sensor by the tire. Both these technologies generate electrical signals that are proportional to force, and they are continuous or analog signals, that is, they continually vary. So if we think of the signal and we plot force on the vertical axis and time on the horizontal axis, we could generate, as the tire gains contact with the sensor and starts producing an electrical signal, that force signal will increase with respect to time, and then as the tire loses contact with the sensor, the signal degrades and comes back to zero. So what we need to do to use that electrical signal that is generated is to determine some single value of feature about that curve that characterizes the force of the tire that was applied. And that force then represents the proportion of the vehicle weight that is carried by that tire that produced the signal. So many different techniques have been used to characterize the tire force versus time signal. Some of these systems, characterizations, use the maximum force that was measured above a threshold value to indicate the single value force. Others techniques use the change in slope of a tangent to the curve. And when the tangent changes from positive to negative slope, we say that's the single value of force that we're interested in. And other techniques use the total area under the curve. And the total area under the curve was not feasible before we had modern high-speed computers. And so it's probably one of the more intuitive indicators of the force that we use to characterize the tire force that we're interested in. The value that we choose needs to be made proportional to the actual force of the tire or the load on the wheel that caused that generated the signal, and we can scale this force value by using a correlation between known loads generated by test vehicles. The test vehicles are representative of the character of the traffic that we'll be weighing. So the on-site calibration of a WIM system is a very necessary and important part of making a system work correctly. During the calibration process, factors that can be used to adjust the signal magnitude to make it representative are generated, and these factors are used throughout the remaining operation of the WIM system. These factors can be used to compensate for local effects, that is, small variations in the roughness pattern, smoothness pattern, and they can be used to compensate for unusual characteristics of the vehicles that are operated by type, and in general can be applied to make the measured or estimated mass of the vehicle equal to the known mass of the test vehicles. In addition to indicating the load values and weight values of a moving vehicle, the tire force sensor can indicate the longitudinal position of a wheel very accurately in the traffic lane. So we can use the sensor, tire force sensor, as a sensor of position of the vehicle. And if we measure the time required for, say, the front axle of a vehicle to move between one sensor and another downstream sensor that's a known distance away, we can calculate the speed of the vehicle. And then if we know the speed of the vehicle, we can measure the time between successive axle arrivals at the sensor and calculate the distance between those axles. And then we can sum those distances and calculate the wheelbase of the vehicle, that is, the distance from the front axle to the rearmost axle on the vehicle, and use this to check legal axle spacing and axle grouping values. So the tire force sensor can be used in this way to supplement the weight and load data. An efficient arrangement of tire force sensors can use two half lane width sensors. We put one half lane width sensor, maybe 6 feet or 1.8 meters wide, in the left wheel path of the lane, and then downstream, say 5 meters or 16 feet, we put the right hand wheel path sensor in, so we have a known distance between the two sensors, and we can measure the time it takes for the axle to move between those sensors, get speed, and then successive arrivals. So in this way we minimize the number of sensors, the extent of the sensors that we use, and can yet get a lot of information. The fact that we can measure the speed of each axle with this arrangement makes it interesting that we can then calculate whether the vehicle is accelerating or decelerating. And this acceleration or deceleration affects the accuracy of the load estimates that we can make. Some vehicle operators try to fool the system, and so we need to be able to detect acceleration and deceleration to at least alleviate that problem. In order for the WIM system to know which axles belong to which vehicle, we need to have a sensor that indicates the presence of the vehicle at the sensors. So we use inductance loop detector for this purpose. This loop detector is a loop of multi-turn loop of stranded electrical, insulated electrical wire that's buried in a shallow groove in the pavement and sealed up in there, in such a way that when the vehicle mass appears over that sensor, we get a switch closure indication that the vehicle is present. That switch remains closed until the vehicle passes out of the detection zone of the loop detector. So we use one loop detector upstream of the sensors to wake up the sleeping system and tell it that a vehicle is approaching and get ready to receive some data from the sensors. And then we use a second detector to indicate that the vehicle is present over the sensors and that the signals that are generated by the tire force sensors belong to that particular vehicle. Now, we can measure speed with a pair of inductance loop detectors, but the accuracy with which this can be done is not as good as with the tire force sensor. The switch closure times are much more variable, but we can get acceptable measurements of speed from the pair of loop detectors. And some sensor arrangement use a pair of loops and a single sensor all the way across the lane. And when a vehicle passes over the way zone of a WIM system, the on-site computer in the WIM system collects the signal information, the data contained in this signal from all the sensors, loops and tire force sensors, and immediately digitizes that analog signal to make it more usable as a computer device, and stores that raw signal as a part of what's called a vehicle record. Now, the vehicle record is then the data contained in the vehicle record is then immediately processed to calculate, using the appropriate factors and techniques, the wheel loads, estimates of wheel loads and axle loads and axle group loads and axle spacing and all of these values, and also can compute such things as violations of the codes about axle spacing or weights and program an alarm. And so this information, all the computed information is stored on site temporarily as a part of this vehicle record. It also includes a timestamp, that is, when did this event occur, and it has site identification codes. So this on-site record is stored temporarily. Then at an appropriate time, when it's convenient, those vehicle records are transferred to a host computer off-site so that they can be made permanent and can be used for subsequent analysis. But the part of the record that is done immediately is displayed typically on the computer screen, so that it can be used to aid the enforcement and interpretation and operation of the system. Concept 5, the final one, deals with how to procure or buy a WIM system. Normally in the procurement process, the user has to select a site where the system will be installed, and then evaluate the smoothness of the pavement at that site, and of course the alignment, and then specify what quality pavement is going to be provided at this site where the WIM system is going to be installed. There are computer programs available today to use the longitudinal wheel path profile information to qualify a site as suitable for installing a WIM system. But not everyone has the profilometer information available, so selecting a site where the pavement is as smooth as feasible is very important. And the user should quantify the smoothness of the pavement as a part of the specification process. And regardless of whether a profilometer analysis is performed or whether there is just site selection takes place, before the system is actually purchased and installed, the smoothness should be quantified. And one technique that has been used successfully is to use a long straight edge, manually operated, with a gauge plate to feel under the system, under the straight edge. And in this technique, the straight edge is swept, one end of it is swept across the lane laterally, and the gauge plate, which is 6 inches in diameter and 1/8 of an inch thick, is used to gauge underneath the pavement, underneath the straight edge. So if the gauge plate can pass under the straight edge, it indicates a roughness of the pavement there. So our experience has been that if a site is surveyed with a manual straight edge and the gauge plate testing is successful, then we can expect the capable WIM system to perform good service. But if the pavement is rougher than that straight edge measurement, we can't expect the WIM system to perform. Actually, the performance capability of a WIM system is directly related to the smoothness of the pavement at the site at the time the vehicle is weighed. So this smoothness needs to be maintained throughout the operational life of the WIM system at that site. So the first step then is for the user to select a site and then specify the smoothness of the pavement at that site. The smooth pavement section that is going to accommodate the WIM sensors needs to have an extent about maybe 200 feet or 60 meters in advance of the sensors, and then about 100 feet or 30 meters beyond the sensors. And this smooth section is important because as a vehicle approaches on the ordinary pavement, it's oscillating a little bit. And so we put it on this smooth section. It allows the oscillations to damp out, and the vehicle will be moving in a horizontal, no vertical movement throughout the operation. And so the extent of this section is to damp out the oscillations of the vehicle and provide this smooth, no vertical oscillation condition for the moving vehicle. The next step in the procurement process is for the user to prepare a performance type specification that details the features that the WIM system will include and the tolerances in which the values must be measured in order to be acceptable. This specification is not valuable unless a test method for checking the performance of the system is also specified. The user and the vendor need to know what test method will be applied to evaluate the on-site performance of an installed WIM system. So the prepared specification, which will be used to invite competitive bids for the system, has to detail not only the performance requirements, but also the test methods that will be used to evaluate the system. Once the user starts to write a specification, he doesn't have to start with a blank sheet or a blank computer screen. Fortunately, there is a standard specification and test method and user requirements document that is available to guide the user through the process of specification. This standard has been developed and used for many years now, and it guides the user in the process. Of course, you might want to make exceptions to certain features. The user may not want the system to provide some of the possible things that are included in the standard specification. So the user can use the standard by reference. Say, I want a type 1 WIM system according to STM, but I don't want it to measure wheel loads, for example. And it might give examples of other things. But the vendor then, at the same kind, is going to bid on this process, can say, I can provide a system except it will not do this and that. So the ASTM standard specification, which will be described later in this WIM series, the availability, is a good starting place to prepare a specification and to guide the user and the vendor in arriving at a mutually satisfactory contract to provide a WIM system. In this first section of WIM 101, I've talked about some of the very basic concepts of weigh in motion and given some background. Weigh in motion technology continues to develop, and as we get better facilities, better materials, where the weigh in motion process will continue to serve as a valuable tool for weighing vehicles. I appreciate the opportunity to have been able to share some of my experiences over the years with you in developing and discussing these concepts. Thank you.